Hey there, welcome to the Electron X channel. I'm Dave Williams. In this video, I'm going to explain the way that Class B amplifiers work. I have redrawn that BJT circuit down here and I've added a few components, and this is a Class B amplifier. It's an example. There's other different types of circuits, but this would be a push-pull Class B amplifier with an NPN transistor connected to a PNP transistor. The input is split and goes to the base of both of the transistors, and the output is taken at the emitter of both transistors. This point right here is the emitter voltage. It's the emitter voltage for both transistors. And from a DC point of view, so my VEQ point is going to be equal to VCC over 2. This voltage from VCC gets split between transistor 1 here and transistor 2 here. Let me label those two, Q1 and Q2. This particular circuit doesn't show any biasing for the base, but oftentimes what you will see actually will be some resistance here connecting the base to VCC, connecting the bases through a resistor to ground. And this also is going to put the base at half of VCC. From a DC point of view, if the base and the emitter are at the same voltage, then both of these transistors are biased off. And that's one characteristic of a Class B amplifier, is that with no input signal, so in other words, in a DC point of view only, both transistors are biased off. So what does that mean? That means there is no collector current through transistor 1 or through transistor 2. So again, DC point of view, let's summarize this. DC operating point puts the emitter resistors at half of the supply voltage, and the collector current is at 0. Now let's look at what happens when an AC signal is applied here at the input. We'll just look at this qualitatively. So let's say this is a graph of my input voltage, and my input voltage is sinusoidal, and I will draw one cycle of that input sine wave. When the input voltage is 0, the output will also be 0. Then once the input voltage gets above 0.7 volts, so that puts this voltage 0.7 volts above the emitter voltage, then that turns this transistor on, and I will be able to have collector current through this transistor. So until this input gets to about 0.7 volts, I will have no voltage at the output, and then once that happens, then the emitter voltage will be about 0.7 volts less than the base voltage, and then that emitter voltage through this capacitor is applied to the output voltage. So this capacitor is a high pass filter, eliminating the DC offset, so my output voltage will be flat for a little while until that input's above 0.7 volts, and then the output's going to be about 0.7 volts less than the input. And then once the input again gets below 0.7 volts, then the output's back to 0, and then this transistor will be turned off. When the input gets below negative 0.7 volts, then this transistor becomes forward biased. This point is about 0.7 volts less than the emitter on this side, so this transistor becomes forward biased and current's able to flow in this transistor. And that occurs when the input gets below about negative 0.7 volts, and I'll get an output that looks like something like that, and that will carry on and repeat itself over time. Okay, so this gives you an idea of what the output voltage is going to be. This example really highlights one of the key disadvantages of these Class B amplifiers, and that's in this region here, where when there is an input, there still is no output for this small range when the input is from 0.7 volts down to negative 0.7 volts. And this distortion has the special name of crossover distortion. And it's called crossover distortion because it occurs at this point where the input crosses over from positive to negative or from negative to positive. So crossover distortion is a big disadvantage of these Class B amplifiers compared to a Class A amplifier. But a big advantage of these Class B amplifiers is that their efficiency is much higher than a Class A amplifier. Now I want to go through and show you what the maximum efficiency can be for a Class B amplifier like this one. So remember, efficiency is equal to the power out divided by the power in times 100%. The input power is going to be provided by this VCC source. And very simply put, it's going to be the voltage, VCC, times the current provided by the source. So that voltage will be constant, but this ICC is going to be changing. And there's actually two components to that ICC. One of them, let's call this I base bias. So that current is what's going to here, and that's going to be a constant, and that's simply going to be dependent on what resistor values we have here. And for this example, we're going to assume that this is so low as to be 0. Let's say these were 1 mega ohm resistors, so we're looking at microamps or so. Plus the average collector current. Okay, this is a constant. We're saying this part is 0, and so we need to look at what is this IC average. And that IC average is going to be the current that's flowing in this path. And the current that's flowing in this path is going to be determined by how this VE varies. And this VE is going to vary by being 0.7 volts or so less than IB, and it's going to be able to go to swing up to VCC and down to 0 volts. And as the input swings as half the sine wave, the output is also, the VE is going to swing as half the sine wave. And when looking at the load, if we remove that DC offset, we're looking at a swing from 0 up to VCC over 2. So if I was drawing out that IC as a varying voltage over time, it's going to be swinging like this from 0 up to, and this maximum is going to be the maximum voltage across the load divided by the load. And that maximum voltage across the load is going to be half of VCC, because remember this is biased to VCC over 2, divided by RL. This transistor is biased on only half the time, so this is going to look like a half wave rectified sine wave. So we'll see this half the sine wave, and then we'll have 0. And then we'll see half the sine wave, and then we'll have 0. And so if that's our IC as we're seeing it change over time, the IC average will be equal to the peak of that over pi. So this is just the standard equation for a half wave rectified signal. And since we know what the I peak is, we know that this equation is going to be VCC over 2 over RL, so that's my peak current divided by pi. I'll rewrite that better here. VCC over 2 pi RL. So putting this back into my P in equation, I get an equation of P in is going to be equal to VCC squared over 2 pi RL. The output power is the power dissipated by this load resistor here. Different ways that we could write this here. This could be the voltage across the load, RMS, all squared over the RL value. Or I could write this as the peak over the square root of 2. This is all squared, and it's over RL. If I work that out, that's going to be the load, the peak voltage across the load squared over 2RL. The maximum swing at the emitter voltage is VCC, up to VCC and down to 0. When you remove the DC bias of that, or the DC offset of that, you get a voltage across the load that's going to be able to swing up to VCC over 2 and down to negative VCC over 2. So that means my peak voltage is going to be VCC over 2. So to calculate the output power, it's VCC over 2 all squared divided by 2RL. So what is that equal to? Well, just rearranging the equation here, VCC squared over 8RL. Now putting these two equations that I've just calculated back into this equation here, I get my equation for P out, which is VCC squared over 8RL, and the equation for P in was VCC squared over 2 pi RL. A lot of these terms get cancelled. I have a VCC squared on the numerator and on the denominator. I have an RL up here and an RL down here. And now rearranging this equation, the answer for maximum efficiency is equal to 2 pi over 8, and of course times 100%. which is approximately 78.5%. And this maximum efficiency occurs when I have the maximum swing across RL, so going up to VCC over 2 and down to negative VCC over 2. And also when I assume that my power that is used by my resistors over here is all ignored. So that gives you a bit of an overview of how Class B amplifiers work, as well as how you calculate efficiency for a Class B amplifier. Thanks for watching, and I will see you in the next video.